There's a rough rule of thumb in public finance that an increase of a tax by factor k will cause the deadweight loss to increase by factor k squared. There's a second rule of thumb that says that the tax revenues that we collect from taxes initially increase as tax rates rise, but eventually decrease. That relationship is called the Laffer curve. We'll illustrate all this in the following panels. We'll begin with a linear demand and supply curve in the market, and we'll assume that we can interpret the demand curve as a marginal willingness to pay curve, and thus illustrate consumer surplus on that curve. We'll begin with an initial per unit tax T that's equal to the magenta line that's inserted next to the original equilibrium and creates the shaded deadweight loss after the new market quantity xt is reached. We then double the tax rate to 2t and see how the deadweight loss triangle expands by the magenta area. Notice that the magenta area is 3 times the size of the blue area, and thus as we increased the tax rate by a factor of 2, we caused the deadweight loss to increase by a factor of 4. As we increase the tax rate further, each time the addition to the deadweight loss is larger than it was for the previous increase. In panel B, we then graph the relationship between the tax rate on the horizontal axis and the deadweight loss on the vertical. We start with the initial tax rate T and calculate a deadweight loss of 1,000. This assumes that the two triangles that compose the shaded blue area in panel A are each worth $500. When the tax increases to 2t, the shaded area that composes the deadweight loss, in other words the magenta and the blue shaded areas in panel A, sum to 4,000. As we keep doing this for each of the tax rates from panel A, we illustrate the relationship between tax rates and deadweight loss as one that's not only increasing, but increasing at an increasing rate. We can similarly illustrate the relationship between tax rates on the horizontal axis and tax revenue on the vertical. When the tax rate is T, we see that the tax revenue in panel A is composed of 12 different squares, each square being worth $1,000. Thus tax revenue at the initial tax rate T is 12,000. When the tax rate goes to 2T, we see that tax revenue in panel A is composed of 20 different squares, each worth $1,000. Thus tax revenue goes to 20,000. As we keep doing this for the different tax rates, we see that what emerges is an inverse U-shape for the relationship between tax rates and tax revenues. This relationship is commonly known as the Laffer curve. If all that we cared about is tax revenue, then the Laffer curve tells us there's an optimal tax rate that maximizes that revenue, and that optimal tax rate will lie below the higher tax rates that will actually lead to less revenue. If, on the other hand, we care about deadweight loss, panel B tells us that this deadweight loss will increase at an increasing rate as we increase tax rates, and this leads to the common policy advice that it's better to have low tax rates over a large tax base rather than high tax rates over a smaller tax base.